Okay, in this video, we are discussing about Ampere's law. So Ampere's law is a simplified version of PHY that is used in some systems with symmetries. Okay, so let's see the equations and definition. So on the left-hand side of the equation, we have the loop integral. Let's say the loop integral of B, or magnetic field, along the curvature or along the line. Okay, so we are considering the loop that is called the Ampere loop. Okay, we define the Ampere loop so that the system is symmetric, and we might get the constant magnetic field, and then when we get the constant magnetic field, it is easy to derive the integral on the left hand side. And on the right hand side, it is the product between the constant mu zero, which is the permeability, and the I enclosed, or all the current enclosed by that Ampere loop. Okay, so let's see the first example on the infinite wire. Okay, so for the infinite wire, we consider the current I. Okay, and then as we look at the set of points about the current and about the circle here, so we can see that for each point, the magnetic field, like at this point B, at this point B, at this point, and at this point, all the magnetic fields are the same. Okay, because of the symmetry of the system. So that when I write down this loop integral B dl. Okay, so this integrate B dl along the curve will just be simplified into the magnetic field B and times by the circumference of the circle, okay, times by the length of the path, which is 2 pi r. Okay, yeah, because B is constant. Okay, and then on the right hand side, within the Ampere loop, and the I that is enclosed within the loop will be just I. Okay, so we substitute I into the equation, and finally we should be able to find that the magnitude of the magnetic field is mu 0 I divided by 2 pi r. So these results agree with what we have from the PHY law that we have done in the earlier video clip. Okay, so the second system is a solenoid. So a solenoid is many loops of wire, okay, that is making a coil, and it looks like a cylinder shape. Okay, so what happens in the solenoid is the magnetic field within the solenoid is so intense compared to the magnetic field outside. So we are going to approximate the magnetic field outside the solenoid as 0. Okay, so we say that the magnetic field is 0 here and here. And then we will define an Ampere loop for a solenoid. So the Ampere loop here is defined as this rectangle. Okay, so it is the Ampere loop with the size L, with the length L. Okay, so if we try to do this integral, okay, as we also assume that the magnetic field within the solenoid is uniform. So again, B is a constant. So when B is a constant, this integral can be simplified into just the into just the product of B within the solenoid and the length that we have given. Okay, and also if we try to go along the whole loop, okay, we also have B outside and times by L, which is approximately 0. Okay, so that on the left hand side we just get BL, and on the right hand side it is mu 0 equals to I enclosed. Okay, so we need to see that the current that is enclosed by the Ampere loop. Okay, there are a lot of current lines within it. So we are going to say that the current is the number of turns. So 1, 2, 3, 4, 5. This is the number of turns. So it is the number of turns times by the actual current. So if I is a current of one wire, okay, so this Ampere loop is considered more than one wire. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we just say that n is 8 in this picture. Okay, so that on the right hand side, I enclosed is Ni, and mu 0 is still a constant, and so that we have the magnitude of magnetic field as mu Ni over L. So sometimes we call this N over L just simply small n, and small n is the density of the solenoid. So density of the solenoid is the number of turns per unit length. Okay, so it just be just mu Ni. So that is the magnetic field from the solenoid. Okay, then the third case is a toroid. So a toroid is simply just like a solenoid, but the coil of wire is made in a donut shape. Okay, so when we consider the Ampere loop, okay, so this loop is the Ampere loop, and here is what has been enclosed in the Ampere loop. So we get the current and times by the number of turns as the I enclosed. So we have I enclosed as Ni, simply Ni again. Okay. Then using Ampere's law, integrate B dl equals mu I. So integrate B dl will be B times by the circumference of the Ampere loop, which is 2 pi r. Okay, and equals to, so this is I enclosed, so equals to mu times by the I enclosed, and the I enclosed here will be the number of turns for the toroid, so it will be Ni, and then B would be mu Ni over 2 pi r. So this is the magnetic field of the toroid. Okay, so that what we have done here is we consider some system that has symmetry. So what does the symmetry mean? Symmetry means that the system that we can define the Ampere loop, and after we define the Ampere loop, we come up with constant magnetic fields every time. So when we come up with constant magnetic fields, we can perform this integral very easily, and after we perform the integral on the left hand side of the equation, we can try and find the magnitude of the magnetic fields of three cases as shown.